the grade is not here today, so. Okay, so what I want to do before going into the analysis of the wazoo is I want to finish the alternative to the proof of step 3. So this is the framework we had. We had these nice transformations. These were automorphisms of the unit disk, and they mapped 0 to alpha and alpha to 0. So beta is some number less than 1 in absolute value. Okay, so I'm using beta not alpha here. C beta prime of 0 is just negative 1 plus beta squared. In absolute value, C beta prime at beta is negative 1 over 1 minus beta squared. And so we can form this new function, big F, related to our function little f by taking this nice composition. And so think of G as the square root function. And so we showed we could always rotate, so we can assume that our number alpha is on the real line. And we can assume it has positive on the real line. So G of alpha is going to be square root of alpha. Its derivative is 1 over 2 square root of alpha. And the goal in step 2 of the proof of the Riemann mapping theorem was to create a function with a certain maximality. It had the largest derivative in absolute value at the origin. Of all maps from the unit disk to the disk that are that are 1 to 1 into and have f of 0 equals 0. So we were going to show that this had a larger derivative at the origin. And of course, one way to do this was to use the Schwarz lemma. And so the Schwarz lemma, we looked at the inverse of this function, and we showed, according to the Schwarz lemma, its derivative was less than 1 because it's not a rotation, and then we're done. But there's no need to directly appeal to the Schwarz lemma. Let's just calculate the derivatives. And so in fact, I believe that we can completely avoid using the Schwarz lemma for the proof of step 3. So why do we still do the Schwarz lemma? It's still a good thing to know. It's a nice thing about the properties of complex analytic maps. So let's just look at what happens. So we have big F prime of 0. So the first is C G alpha G alpha. So that's taking beta to be G alpha. G alpha is square root of alpha. So I'm just going to do absolute values. So I don't really care about anything other than absolute values. So the C G alpha is going to, at G alpha is going to just become 1 over 1 minus, and now beta is the square root of alpha, so we get minus alpha. Right? Because the square root of alpha squared is just alpha. Alright, the next one is G prime of alpha. Well, G prime of alpha is 1 over 2 square roots of alpha. The next is C alpha prime of 0, which is, it's negative 1 plus alpha squared. Since we only care about absolute values, it's 1 minus alpha squared. And now we multiply by f prime of 0. So all we have to do is show that this gobbledygook in the beginning is greater than 1 in absolute value. Is there something we can do if you look at this? What can we do? Yes. Cancel. Right? Don't resort to mathematics. We have a 1 minus alpha squared. That's 1 minus alpha, 1 plus alpha. Okay? We can write this now as 1 plus alpha over 2 square roots of alpha times f prime of 0. So all we need to know is 1 plus alpha over 2 root alpha greater than 1? And if so, we have a contradiction. So is 1 plus alpha over 2 greater than square roots of alpha? No? You can just check it, right? And so you can go down to Mathematica and plot it, or you can go to a Calc 1 student, have them plot it, right? Have any of you seen this before? I'm sorry?
It's root alpha minus 1 squared. Greater than 0.
So there's a name for this inequality. This is one of the most famous inequalities in all mathematics. AMGM. The arithmetic mean geometric mean inequality. The arithmetic mean of two numbers is greater than or equal to the geometric mean of the two numbers. And equality only holds if they're all the same. How should I really write square root of alpha? Yes! Well, what else do I do? It's either that or I add 0, and I wouldn't add 0 here. I multiply by 1. So I'm calculating the geometric mean of two numbers, 1 and alpha, and I'm calculating the arithmetic mean. And so the claim is the geometric mean is always less than or equal to the arithmetic. You have equality only if they're the same. So proof, there's lots of different proofs. let's look at 1 plus alpha versus 2 square roots of alpha. And without loss of generality, we can assume alpha is greater than or equal to 0. Because if alpha was negative, this would be absurd, right? I'm not taking square roots of negative numbers and comparing a real number to an imaginary number. So alpha is greater than or equal to 0. Well, if I square both sides, I get 1 plus 2 alpha plus alpha squared versus 4 alpha. So if I subtract, I get 1 minus 2 alpha plus alpha squared versus 0. But what's 1 minus 2 alpha plus alpha squared? 1 minus alpha squared. And which would you rather have, 1 minus alpha squared or 0?
Of what?
Of M&Ms. I will assume nobody is doing a heavy diet right now. Of dollar bills. 1 minus alpha squared, right? 1 minus alpha squared can't be negative. So it's always greater than or equal to 0. What's the only way 1 minus alpha squared could equal 0?
Alpha equals 1.
Alpha equals 1. So that if the two numbers are the same. And so the general case is x1 plus xn over n is greater than or equal to the nth root of x1, xn. All the xi's are greater than or equal to 0, and equality if and only if xi equals xj for all I and j. Or if you want for all I not equal to j. Okay? So that's the arithmetic geometric mean. And so what I like is, this gives you a little bit of a sense of what this map is doing. So it's this, in a sense, it's the same proof as is in the book. You know, I don't get credit for an original proof of step 3 of the Riemann mapping theorem. It's just when I was reading the proof, it seemed very unmotivated. Why are we doing this? So good things to look at is, why did we take the square root function? Could we have done a cube root? Could we have done a fourth root? What could we put there and still have the proof work? Was there something special about the square root? What were we doing? We were trying to say, if it wasn't onto, then there was some point we missed, and we could somehow come up with a new function where we expand the derivative just a little bit. And so when you look and see how the derivatives of these functions interact, you can now see explicitly how we got the derivative to be just a little bit larger. Okay? So we've now finished step 3 of the Schwartz theorem, I'm sorry, the Riemann mapping theorem, and we've now removed all references to the Schwartz lemma. Okay? Any questions about step 3? Okay. So now it is time to go back to step 2. And so step 2 is the most difficult step in the proof of the Riemann mapping theorem. And it is a lot of notation and a lot of results from analysis. I'm going to try to split it up so that we don't do all the analysis in one day. We're going to try to do it over 2 days. So we need a couple of things. The first is a bunch of definitions. So can someone tell me what is a normal family? Yes?
It's a family of homomorphic functions such that any sequence in it has a subsequence that converges uniformly for compact sets.
Does everyone agree with that definition? I don't think that's what I have.
I don't think you need the compact sets. You just need
Well, you do need convergence on compact sets.
Every sequence has a subsequence that converges uniformly on the compact.
So how is that different than what Dan said?
I think it was the same.
I'm sorry?
He didn't say on every compact subset of omega.
He might have missed it. I was fixated on something else.
Can you repeat that again?
Word for word. No changes. Alright, so let F be a family of homomorphic functions. It is a normal family if for any sequence in it it has a subsequence that converges uniformly within a compact set.
Okay.
I'm a little off somewhere.
You're one word off.
Oh, wait, never mind. I'm not sure.
Did we need more?
No. You can define the notion of a normal family without restricting to holomorphic functions, right? We're only going to care about, yes?
On every compact subset of omega?
Yes. So, you take any compact set, and the family will have a sequence that converges uniformly on that compact set. It could be a different sequence on different compact sets. One of the things I do not like about the book is that in its constants, they don't include subscripts that show the constants depend on the compact set. So in class, we're going to put in extra subscripts so that we remind ourselves this is a constant for this compact set. So any sequence of functions in F, well, any in F has a subsequence which converges uniformly on compactor. And what uniformly on compactor means is you give me any compact set, the convergence on that compact set is uniform. The nice thing about uniform convergence is it doesn't depend on the location of the point. So the definition of continuity, given a point x, for all epsilon greater than 0, there exists a delta. Much better notation would be for any x, for all epsilon greater than 0, there exists a delta which may depend on x and epsilon, such that. So when you do the notion of continuity, the delta in the notion of continuity has an x and an epsilon subscript. We ignore those, we omit those, but they're really there. All right. Second definition is uniformly bounded. And we might just do this on compactor. So what does it mean to be uniformly bounded on compact sets? If you have to speak up in class, this is the one to go for.
All the functions are bounded by the same bound.
All the functions are bounded by the same bound. And what can that bound depend on?
What's the set?
I'm sorry?
On your set?
On the set. So,
Oh, okay.
given a compact K, there exists a BK such that for all Z in omega, in K, and for all F in our family, the absolute value of F of Z is less than or equal to B sub K. And again, I just like putting in the subscript K to remind ourselves that this is coming from that compact set K. In a lot of the proofs, we're going to be switching which sets we look at. And it's very easy to accidentally be on the wrong set. Alright, so the last one we need is equicontinuous. Equicontinuous. So what does it mean for a family to be equicontinuous?
Given epsilon greater than 0, there exists a delta greater than 0, such that when when z and w is the magnitude of z minus w is less than delta and greater than 0, f of z minus f of w is less than epsilon in magnitude.
For all f in a family. So I removed one thing you said.
Shouldn't that be
The-
delta?
Yes.
Z minus w greater than
Sorry.
0? Or,
Yes.
yes.
It's okay if z minus w is 0.
Okay.
Why is it okay if z minus w is 0?
Because it's still the same words.
Because 0 is less than epsilon. So you would think about the definition of the derivative,
Right, yeah.
which is, it's very important in the definition of the derivative that you say z and w are never equal. But here, we do allow them to be equal. That's actually the easy case to handle. Okay, so these are the three big definitions we need. So whenever you see definitions, what should you do?
Think away conditions.
That's theorems.
Think of it as how.
Or babies in candy.
Delta depends on epsilon in that thing, right?
Delta would depend on epsilon, yes. And in fact, what else would delta depend on? And what else?
Could also depend on Z and W.
No, we don't want it to depend on Z and W.
Oh, right.
But it can depend on K. So again, it's really good to be explicit. We fixed a compact set K, we fixed an epsilon greater than 0, given that there is some delta. Okay, so we've got all these definitions now. Now that we have these definitions, what should we do? Yeah, examples, right? Can you give me any examples of these things? If not, these are probably not good definitions to study. Okay, so the first one is a normal family. Any sequence of functions has a subsequence which converges uniformly on a compactor. So let's take maybe for one, maybe omega is the open interval 0, 1, and maybe fn of x is x to the n. Do you think that this is a normal family? So given any compact set, can I find a subsequence of functions that converges uniformly?
Excluding the endpoint.
I am excluding the endpoints in my omega.
I think that looks okay too.
Because I've excluded the endpoint, what does each function go to?
0.
Each function goes to 0. So here you're okay. This is normal. But now, if I do omega is 0, 1, and fn of x is x to the n, is this normal? No, because now every function is going to converge to 1 at 1, and anything less than 1 is going to converge to 0. So this would not be normal. Let's look at omega is 0, 1 again, and fn of x is the sine of nx. What do you think?
Not normal.
Not normal. So this one's not as clear, right? So the question is, can I find some subsequence where it's converging? And so what if I have n equals m plus 2 pi l plus small l. What if I had something like that? Then the sine of nx is almost the sine of mx, because they essentially differ by, well, but then I've got to hold true for all values of x. This would be true maybe when x equals 1, but it's got to be true for all values of x. And so you're okay if x equals 1, but all x, unlikely. So I do not think that this would be a normal set. What nice property, though, would 3 have? So it's not normal, but yeah, it's at least uniformly bounded. You know, at least uniformly bounded. What if instead I let omega be the set of all z, absolute value of z is less than 1, and fn of x equal the sine of, fn of z be the sine of nz. Could this be normal? So what do you think? Could it be normal? So I'm now looking at it on the unit disk. I'm considering it a function of a complex variable rather than a function of a real variable. Could this be normal? Yes, no, or unlikely?
Unlikely,
Unlikely. Why unlikely?
because it contains the real line.
Yeah.
So that's a subsequence that
Right.
doesn't converge.
It's just a special case of 3. Oh, I'm sorry, 3 is just a special case of it. So if this is not going to converge along the real axis, this will also have problems converging on the real axis. So unlikely that it's normal. Unlikely to be normal. Alright, what about uniformly bounded? Do you think it's uniformly bounded?
No.
So sine of nz is going to be e to the I nz minus e to the minus I nz all over 2i. So for what values of z will this be bad? And what wave for z close to 0? Because if z is a small real number, we're fine. We showed in part 3 that it was uniformly bounded. So which z would be dangerous?
Purely imaginary.
Purely imaginary. If you come down along the imaginary axis. So if you take z equals plus or minus 1 over m. As m gets closer and closer to 0, the problem is now the m is going to...
I don't think you need the m. You have the n over there, right?
Well, no, I need z to be a small and fixed number, and then let n go to infinity. Because I've got to be... Although, actually, no, wait, I'm trying to show it's not uniformly bounded, yeah. I can take m equals 2. It would just be shown inside the disk. Okay, right. I don't need to have m getting small, thank you. And now as m gets very, very large, it's going to explode. So we see, there's differences in behavior between real functions and complex analytic functions. Right? Yes.
Could you use Liouville's theorem here? That it's not a constant function, so it can't be bounded.
Well, what do I need if I want to invoke Liouville? I like invoking Liouville, but what do I need?
Entire.
Entire. It's going to be
Okay.
defined on the entire space.
Okay.
And so unfortunately, I'm only defined here on the unit disk. Okay, so at least we have a couple of examples in our mind to think of when we hear about these different functions. I'm going to do things in a slightly different order, and I'm going to just state a lemma right now that will be useful. I'm going to try to keep the definitions on the board because these are going to be so useful in what we're doing. So what I want to talk about is the method of exhaustion. So we're not going to need this until Friday's class, but let's get it in the bank now because Friday's lecture is going to be a little bit more involved. So, lemma. If omega is open, there exists a sequence of compact sets K sub L such that K sub L is contained in KL plus 1 is contained in omega, and the union of the KL equals omega. So I can write any open set as a union of compact sets. Basically think of it as inflating a balloon. It's going to expand out and fill the whole set. This is not a complex analysis result. This is just a general analysis topology result. And what's nice is we can actually give it an explicit construction of such sets. Okay, so proof. So case 1, assume omega is, what would be a nice thing to assume about omega? bounded. And then we'll show that we can remove the boundedness. Then we just let KL be the set of all x in omega such that the distance from x to the boundary of omega is greater than or equal to 1 over L. So it's all the points that are at least 1 over L units away from the boundary,
Distance from x
to the boundary of omega.
Oh, the boundary.
So d omega means boundary of omega. So if you want, we often use dots to indicate that we don't include the boundary. So what I might do here is I'll draw something like this. And, well, more like this. And so this distance here, everywhere should be 1 over L. And so it should be clear that as L gets larger, you can't have points leaving your region. So KL plus 1 will clearly contain KL. And then in the limit, you'll get everything. Because you're an open set, you give me any point, it's some distance away from the boundary. Why? The boundary of the open set is compact, and so we have this beautiful result. If you have a continuous function on a compact set, it attains its maximum and minimum. Right? So this is one of the big results we need from analysis. A continuous function on a compact set attains its maximum and minimum. You give me any point in my set, and I look at its distance to every point on the boundary. That's a continuous function on a compact set. It has to attain its maximum and minimum. So there has to be a minimum distance. So if I choose L sufficiently large, that's going to be in one of the KLs. So you have to just put in the proof. So we use a continuous function on a compact set attains its minimum. Okay, so that's a nice result from analysis. This is one of the places where we need to use it. But now we have the other case, case 2, omega not bounded. Then all we do is replace KL with KL intersect the set of all x, the absolute value of x is less than or equal to L. So all we do now is if our set is not bounded, so let's say now that this is our set omega, what we do now is we have our 1 over L there, and now we just take a circle of radius L, and we look at the intersection. And so now in this case, that would be the region. And again, you can just go through and say, and see that everything is going to work out because these will keep expanding and expanding and expanding. You give me any point, it's a certain distance away from the origin. And so eventually it will come into play. Okay. Any questions about proof from exhaustion? So why do you think we care about proof by exhaustion? Why are we using it? Why are we deducing these results?
We have all the results about compact sets.
Good, we have all these results about compact sets. We want to somehow piece it together. Right? So we want to be able to do our analysis on compact sets. Why do you want to do your analysis on compact sets?
We have nice properties.
We have nice properties. We have great convergence properties. What's the first thing that comes to your mind when you think of compact sets?
Closed and bounded.
Closed and bounded. To me, it's John Lackey's arm tonight, but my thoughts are a little bit elsewhere. What's a nice property compact sets have?
What you just said.
It attains its max.
I'm sorry?
Attains its max.
It attains its max. But there's another way of defining a compact set.
The subsequences.
Another one is subsequences. There's something else, though. There's so many nice things about compact sets. So this is just a great way to review what do you know about compact sets and why do you like them.
Open cover is finite.
Open covers, right? Any open cover has a finite subcover. We like open sets. Whenever we do something about a property, about continuity, about differentiability, it's always a local condition. And if you want to piece to something global, you want to tie in together all these different local facts. Well, if your set is compact, any open cover has a finite subcover. So you take a bunch of key points and understand what's going on about each one of those points. Then you only need finitely many of them for their union to be everything. And then you can somehow choose your deltas involving a minimum of a finite number of things, and everything will be well defined. So this gives you hopefully some idea of where the proof is going. If you look at all of our definitions here, we're talking about z minus w less than delta, or delta epsilon k. And we're going to want to tie in together a lot of different points, and this is why compact sets are going to be so useful. Okay, so now it's Montel's theorem. There are two parts. I'm only going to do part one today. And so part one is holomorphic family, uniform bounded compactor, equicontinuous implied. Okay. So F is holomorphic. So now we're going to use your holomorphicity. And this is something that is not true if we drop holomorphicity. So F is holomorphic, uniformly bounded on compactors, on compact sets. Then F is equicontinuous on compact sets. Okay. What do you think happens if we drop the word holomorphic? So imagine we have a set of functions that are uniformly bounded on compact sets. Then it's uniformly continuous. What do you think?
You could have something going to a step function.
So we could have something going to a step function. So the result is going to fail if we drop holomorphic. This part of the proof is crucially a complex analytic proof. It's not the case for real value, for real functions. So for example, let's let omega be 0, 1, and fn of x is x to the n. Okay. Then we don't have equicontinuity. So now we have to think, is this a good example? Do you think this is a good example? You like this example?
Well, if we're considering real values, it's bounded on that set, which
Okay.
is a compact set. And fn of x are all differentiable in the real sense.
Okay. So what about the following? Omega is 0, 1. Fn of z is z to the n. Those are holomorphic functions.
Doesn't Montel's need normal too?
That's the second part of Montel, that it's a normal set. So what's wrong with the function f of n of z is z to the n? Very subtle difference. What kind of sets do we study? When we're doing the Riemann mapping theorem, what kind of sets are we studying? Open sets. So I'm giving you right now an example of a space where my set is not open. So what I could do, a better example is omega is 0, 2, and Fn of x equals x to the n if x is less than or equal to 1, and 1 if x is greater than 1. That,
Can you explain that one more time? Why doesn't apply, or why we can't use this function?
well, we're always doing families are defined on open sets. 0, 1 is not an open set.
Oh, I see.
And that's why there's going to be issues here, because it
Oh,
attains...
because it's an open set, but we want compact subsets of an open set. Okay.
Right. And so if I include the point 1, then a compact set could be 1/2 1. And so I want to study open sets. So if I consider now omega equals 0, 2, and I take this function, like this with a kink, now I will have issues. But what's wrong? Why might this be a bad example? Yeah, it doesn't have differentiability at the point 1. So again, polymorphic is a lot more than just differentiable. It's infinitely differentiable. So maybe a fair real analog to look at this is maybe I have a function, a family of functions, where the functions are only differentiable once. And if the functions are differentiable once, can you do something like this? So now some of it might come into what can you say about the derivatives of the functions in the family. So now, consider family of real differentiable functions. And again, I want to deliberately go slowly through the proof of all this stuff. I don't want to rush through. There's a lot of good analytic stuff here. If it ends up taking us to Monday next week to finish this, that's fine. I want you to be really thinking about the different conditions, what they mean, what the consequences are. You should never just read math definitions and go, oh, that's a nice, and just keep going. You should always stop and try to come up with examples. You should see, if I throw away this condition, what do I get? Can I somehow get a reasonable example? What's the correct analog? What can I build my intuition on? So let's consider a family of real differentiable functions. Well, as soon as I tell you the functions are differentiable, what do you want to know?
How many times?
How many times? So I'll say once.
Where are they differentiable?
Well, I'll say everywhere.
Okay.
So differentiable everywhere, and you can only assume they're differentiable once. But maybe there's something else you could assume about the derivative.
It's non-zero.
Oh, a fuzzy zero derivative is fine.
Okay.
That just means it's locally lazy.
It's not infinity.
Okay? You have to be a little bit more specific on not infinity. Because if it's differentiable, it's not infinity.
I'm going to infinity?
It's not going to infinity. So what if the derivatives were bounded? So what if all the derivatives are uniformly bounded on compact sets? So what if derivatives are uniformly bounded on compact sets? So what would happen in that case? Then you'll be okay. F of x minus f of y, how can I write that? What theorem can I use to understand f of x minus f of y? These are real functions. So you want to understand f of x minus f of y. How far could f of x be from f of y? What theorem do we have from Calc 1, Calc 2?
Oh, the max. Is the max is equal to the maximum derivative times x.
Yeah. And instead of using the maximum derivative, you could even be a little bit more specific. It's equal to, what theorem do we use? One of my favorite theorems in Calc 1. How many of you have watched the TV show Friends? Except for the first and the last episode, what does every episode of Friends have in common?
Title.
The title.
The
The
one
title,
with-
the title is the one with. When I teach integration, when I give a proof of the fundamental theorem of calculus, I title it the one with the mean value theorem. And you can just keep using the mean value theorem, mean value theorem, mean value theorem. When in doubt, use the mean value theorem. And so here, by the mean value theorem, this is just f prime at some intermediate point, called cxy, times x minus y. But if it's uniformly bounded on compact sets, that's less than or equal to bk x minus y. And so if you just choose delta to be less than epsilon over bk, you're done. So if delta is less than epsilon over bk, you're okay. If you want to be really pedantic and safe, write bk plus 1. Why would you write bk plus 1? In case b is 0. Now, it would be strange to have a set of functions whose derivative is uniformly bounded by 0. That could happen, and in this way your delta is at least finite. The other thing is then you'll get something that's strictly less than epsilon, rather than less than or equal to epsilon. And remember, your goal was to show less than epsilon, not less than or equal to epsilon. Okay? There are some really anal graders for this matter still. Okay? But always give yourself a little bit of a slush factor. Except, of course, when I'm handing in receipts. Okay, so this is a really good example of how things change in real and to see how much do we really need holomorphic. Is it enough for the function to be differentiable? So can you give me an example of functions where the first derivative is not uniformly bounded? And then maybe you're having some kind of problem. So again, if the functions are differentiable and the derivative is uniformly bounded, then we're going to be fine. And it's just the mean value theorem. Okay? At least it's the mean value theorem if we have functions of a real variable. Do we have the mean value theorem in several dimensions? There are analogs to the mean value theorem, but it's not quite as nice. And you can try to look at a path between 2 points and talk about the gradient and it's some intermediate thing, but it's not nearly as nice. If you've read Baby Rudin or the Blue Book, Principles of Mathematical Analysis, they have a nice section in one of the chapters where they talk about how the mean value theorem generalizes. Okay, so today we've got the definitions, we've got the statement of the first thing we want to go to, that f is holomorphic uniformly bounded on compact sets, and we've explored a little bit about consequences of these statements. What would be some examples of these things? What would not be? So we have about 5 minutes left. I do not... Oh, 7 minutes left. Even better. I really don't want to rush through the proof of Montel 1 in 7 minutes. So instead what I want to do is talk a little bit about other convergence questions and just try to put this lecture into a more general framework. And then we'll prove Montel 1 on Friday and maybe prove Montel 2 on Friday, but probably we won't finish Montel 2 until Monday. And then what I'll do is I'm going to just supplement with a few just general facts. So I want to talk a little bit about Fourier series. And we'll be looking at analogs of this when we get to, the quantum part of the course. How many of you have seen Fourier series before? How many of you have not seen Fourier series before? How many of you are not sure if you've seen Fourier series before? Okay, so this is basically, think of it as an analog or a generalization of Taylor series. And the idea with Taylor series is we try to replace a complicated function with simpler functions that are easy to understand. So we want to replace, instead of 1x squared, we're going to use 1 sine x, sine 2, well I'll do it this way, sine x, cosine x, sine 2x, cosine 2x, and so on and so on and so on. So instead of using 1x squared, we're going to use sines and cosines. And instead of using sines and cosines, we could also use instead 1 e to the ix, e to the 2ix, e to the 3ix, and so on and so on and so on. And actually, we should really include also minus ix, and then 2ix, and e to the minus 2ix. And if we include the minuses, we can get sines and cosines by taking appropriate combinations. Taking appropriate combinations of sines and cosines will give us those exponentials. So really, we can study either one. And the idea is that this is a much better basis to use than this. And so, defining it like this, my interval is 0 to 2 pi, or 0 to 2 pi, or you can often do minus pi to pi. If you want to be in, you do minus pi halves to 3 pi over 2. You basically take a window of length 2 pi. If you don't want to deal with 2 pi, you just replace all the x's with 2 pi x. And it just depends, where do you want to normalize, how do you want to choose your variables. Not a big deal. And the goal is to say f of x is a sum of an e to the I n x, and goes from minus infinity to infinity. Now what's really nice is the integral of e to the I n x times e to the minus I mx. If you integrate from 0 to infinity, what do you think this equals? Can you give me any values of n and m where this is easy to calculate? Oh, we don't want to go to infinity.
0.
Let's go to 2 pi.
N equals m. Yeah.
Yes, if n equals m, we get 2 pi. And if n doesn't equal m, 0. What does this remind you of? Orthogonality. That these functions are orthogonal to each other. If we want to make them orthonormal, we would divide by square root of 2 pi. Or we would say, screw this, let's just look at the intervals 0 to 1 rather than 0 to 2 pi. So it's where do you want your pi's to be? I would much rather put my pi's in here and not have to divide my functions by square root of 2 pi. That just feels wrong to me. Okay? It just cleans which formula do you want to be clean. We can actually figure out what an is. If I take f of x, and I integrate by e to the minus I mx from 0 to 2 pi, and then I divide by 2 pi, if this expansion exists, what will that be? Almost. A sub what?
Or m.
A sub m. Assuming I can interchange the sum and the integral, assuming the function is given by the series expansion. So there's a huge number of convergence questions. When is a function given by its series expansion? What kind of convergence properties does the series expansion have to the original function? If my original function is continuous, does this work? Does this converge to the original function wherever my function is continuous? If my function is not continuous, I expect there to be issues. And so one of the most famous examples is the Gibbs overshoot, where if you have a discontinuity, how many of you have seen Gibbs overshoot? How many of you know where Gibbs is from? Spent almost an entire life at Yale and New Haven. One of the first American scientists of note. Even his grave is still there. Never really traveled much. Gibbs overshoot. Okay? So interestingly, at a point of discontinuity, you're overshooting. I think right at the very center, you will be halfway between, but a little bit to the left and a little bit to the right, you've actually dipped down and dipped up. So when you think about how the signs are going, think of it as rounding bases. Sometimes which path do you take? A little bit to go down and come up like this. Then you can start to ask, well, if f has certain properties, what properties are inherited by this sum, and when does this sum exist? If my function is continuous, if my function is differentiable, if my function is L1, which means the integral of the absolute value of f is finite, if my function is L2, the integral of f squared is finite. And so the big result is Collison's theorem, which talks about if you have a function which is L2, then the Fourier series converges almost everywhere. If the function is L1, you can have a Fourier series that diverges, I believe, almost everywhere to the original function. believe Kolmogorov found a strange example. So L1 convergence is not as strong as L2 convergence. How many of you have heard phrases like L1, L2? For the astrophysicists, how many of you have heard L1, L2, L3? I think they go up maybe to L5. And the astrophysicists here? The Lagrangian points for the orbits, right? Does it go up to 5? Anybody else? I know there's at least 3 of them. And if you look at bodies orbiting, Jupiter has certain dust clouds at certain places because of the way the gravitational stuff goes. Depending on what kind of properties F has, you get better convergence. And so all the stuff we were talking about today, about this uniform convergence, here's the more general case. I want to know what kind of convergence do I have on the sequence. More generally, rather than looking at the Fourier series, we can look at other series that have better convergence properties. Alright, so this is a good place to stop. We will continue on Wednesday with proof of Montel 1.